We'll just finish off some stuff that was left over from last week. Quiet, please. Okay, so we'll finish off some stuff left over from last week and then move on to talk a little bit more about some other things in inheritance. Can you hear me if I turn the volume down so we get rid of this hum? Can you still hear me? Okay. So this is where the last thing that we did on Thursday, where we were looking at how some system methods can be overridden. One that we've looked at before is the two-string method for printing. And also, Java assumes that the object class, which is the top of the inheritance hierarchy, has an equals method. So here's an example of if we have a student record that has three fields like a name, an ID, which is also a string, and number of credits or number of units that you've done, which is also, which is an integer, that if you have two student records and you want to compare them, then the comparison is just if the name is the same, so we're using string equals here, and the ID number is the same, and they have the identical number of credits, they're the same. But before we get to this part, we've got two checks up the top. One is saying, like if we call, the way that we call this is we ask if object X equals object Y. So in other words, if X is a student record, we're calling the equals method in that object and passing to it another object which should be a student record, a student object. So the first thing we're doing is saying, is this object identical to the one we're comparing? In other words, are they actually the same student, the same object? If they are, then we return true immediately. Otherwise, it only makes sense to do this comparison if the two things we're comparing are the same, belong to the same class. So we've got this operator instance of that says if the object is an instance of student, that's the Boolean expression that's true. So if not object instance of student, we return false. In other words, if Y is not a student record, so we can return false. We do this cast to assign this object to a student variable. Do you remember why did we do that? For the few people who were there on Thursday night. Why do we do this assignment here? It's a convenience, but why is it convenient? If we didn't have this assignment here, how would we have to change that code? Sorry? Kind of. What type is obj? Object. So that means that it can be anything at all. Right? Any kind of object at all can be passed into this method. Now, name and ID and credits are fields that belong to the student class. So we can't just say obj.name because obj can be anything. It's not a student, it can be anything. So either we have to do this. Wait a minute. Do we have an eraser? We don't have an eraser. If I want to get to, if I just have the variable obj, and I want to refer to the name of this object, I would first have to cast it as a student. and then get its name. Right? If I try to do obj.name immediately, then Java would object because it would effectively be saying, the error message would be that obj, being just any object at all, doesn't have an identifier field, or at least Java doesn't know about the identifier field. Only student type objects, the name field, only student type objects have names identified as credits. So you have to take obj, and remember that if you put a class name in parentheses in front of the object, then Java will try at runtime to cast that into a student type of object, and then you can access its name and the other fields in there. Right? Now, I would have to do that throughout this whole expression. So just to save me typing, I only need to do this once. I cast obj into a student and assign it to a student object. And then from then on, I can just use this other variable to refer to it because it's a student object. Okay? Does that make sense? This last expression is a conjunction of, the whole thing is a Boolean expression, right? So this, we've declared up the top that equals is a method that returns a Boolean value. And this whole thing, we've got name equals, so remember the double ampersand is a logical AND. So we've got this, and this, and this. If all three are true, then the whole expression returns true. Right? Being a logical AND, if any one of these is false, then the whole expression is false, right? So we can say return this whole complicated expression, and it all reduces to true or false and gets returned. Okay, any questions about this? You understand what the top two things do? Tell me what this keyword means. Can anyone help? What does the this keyword refer to? Can you help her? Yes, you? Yeah, you. It refers to the object itself. So if it's the call x dot equals y, this refers to x, right? The object itself. It's the object that contains this method. So that top one is saying if the parameter object is the double equals means identical. In other words, they're two variables that refer to exactly the same object. If they're identical, then we return true. And remember what instance of is? I was trying to make sure you're all awake. Can you tell me? Instance of, yep. No? Can anyone help there? What does instance of mean? Do you know? No, just the instance of operator. Yep. Right, so we're saying, is obj an instance of student? Because remember that the obj variable, because we've declared it to be object, it can be, an object is at the top of the inheritance hierarchy. It means that obj is allowed to belong to any class at all. It can be a dog, a cat, doesn't matter. So if we want to make sure that the object we're comparing is the same class as the student object, then we can say, is obj an instance of student? Right? So that's a Boolean expression that will be true or false. And obviously true if it is an instance of student. The exclamation mark out the front is a negation, a logical negation. So it means that if this object is not an instance of student, then we should return false. Okay? All right, let's skip this one. A couple of other things about inheritance. There are sometimes, let's have a look at the diagram. Remember that normally, when you declare variables or methods, Up till now, we've declared them as being either public or private. Public meaning, let's say if it's some class there, if we declare something public, it means that everybody in the world can see the variable or method. Right? And normally what we do is we try to declare all the fields private, and we declare public methods for accessing those private fields. Right? The idea being that by declaring those methods, we can sort of control access to the private information. All right? So public means everybody can see it. Private means only the methods in that class can see it. Even the children in the inheritance hierarchy, if it's declared private, even these guys can't see the private stuff in the parent class. Right? Now there's an intermediate form of privacy of these variables where if you declare something in the superclass to be protected rather than private, it means that all the children can see the protected variables or methods in the superclass, but nothing outside of the hierarchy below the parent can see it. Right? You see the distinction? That public means everybody can see it. Private means only the class and its children can see it. But any class that's not a direct descendant of the superclass, like some class, nobody else can see it.
Claude, I think your Ethernet cable's fallen out or something.
It's possibly never even been put in.
Yeah,
Okay.
restart the desktop, is that through?
Sorry?
Restart the desktop, is that through? Or it doesn't want you to do that?
Is that all right?
What's the address on that? 158.82?
Say again?
Can you bring the desktop again back up and bring the address?
Oh, 82 is the last one. 129.94.158.82.
Still can't see that. Yeah, it's got
I'll shut it off and start again.
Yeah, probably.
169.254.137.234. Okay, so getting back to this, the reason you would use protected is there may be times when it's going to be very inconvenient to have stuff private, and the children really need to see stuff that's been declared up above in the parent class, but you still don't want anybody else to see it. Generally, what you should still try to do is make the fields in the superclass private, and even the children should access the fields through accessor classes and mutator classes like you've done before, you know, like get name or set name or something like that. But you might also want to have methods declared as protected because the children should be able to use those methods, but nobody else outside the hierarchy should see it. Okay? So the general principle is try to keep the scope of variables and methods as limited as you possibly can, and only make things public if you really, really need to, like if it really has to be seen externally. And even for the children of in the subclasses, even them, try to restrict how much they see of the superclasses and only use protected if you need to. Okay. So now we'll move on to, whoops. To see a few more examples of the use of inheritance in hopefully some interesting applications. So the example we're using If you want to look this, read about this in the textbook, this is from chapter 10 in the textbook. One of the useful things about object-oriented programming languages is that they're very good for creating simulations. In fact, the very first object-oriented language was a language called Simula that was developed, I think, in the late 60s or something like, oh no, probably 70s. And it was designed for discrete event simulation. And so that's where the idea of object-oriented programming actually started. And we use simulation a lot, and in our case, we're going to use it, apart from getting an idea of how simulation works, to illustrate some additional ideas about the way that inheritance works in Java. We'll talk about abstract classes. These are classes that like parent classes that don't have any actual instances. You'll only ever have instances of subclasses. And then a few other ways of introducing a more complex inheritance. Okay. So you sort of are probably aware of that simulation programs exist. Like, if you want to understand how traffic flow works through Sydney, the RTA has some of the most sophisticated traffic simulators in the world. They were originally developed for before the Sydney Olympics, thinking that the traffic during the Olympics was going to be terrible. They did a lot of simulations and developed a lot of software to control traffic flow. In fact, so many people left the city during the Olympics that traffic was actually great during those 2 weeks. What you're simulating there is queues of cars along streets and what happens to them when they're bunching up along, say, a highway. What happens when they reach an intersection? How does the intersection affect traffic flow? If you've got a roundabout, what do you do? So across the road, I'm not sure if you're aware, across Anzac Parade, there's a research institute called NICTA, and they've been working with the RTA doing a lot of traffic simulation, and they've got some of the fairly clever artificial intelligence control systems experimenting with the busiest roundabout in Australia, which is, I think, Albion Park down towards Wollongong. Weather simulations you know about, because everybody talks about climate models. But it's not just the actual simulation of the weather. Economists simulate carbon. What's the effect of carbon tax going to be on the economy? That kind of stuff. Nuclear processes. Stock market's interesting. People try to predict what happens to the stock market all the time, obviously, to try to make money. And one of the new things that it's happening with the stock market simulations is that you're probably aware that there's a lot of program trading happening. I mean, probably most trades on the stock market are programmed. You know, there are some set of rules that say when a stock reaches this much buy or this much sell and so on. And these things are happening so fast that a lot of the algorithms for this sort of stuff are now being put directly into hardware, so that your algorithm can run 1 microsecond faster than somebody else's algorithm and get in and do the trade before the other guys. So this sort of technology is evolving at a ridiculous rate, and is probably causing as much damage to the stock market as it is creating wealth as well. Because when you start having these trades going so fast, it's pretty hard to figure out what's going on. Most of the time when you're creating simulations, you're making assumptions. It's usually too hard to simulate the real world in detail. In fact, that is the real world if you're in full detail. So you make assumptions to work out how to reduce the complexity of the simulation so it's computed in a reasonable amount of time. The benefits of being able to predict, that's fairly obvious. Let's have a look at an example of the simulation that we're going to play with. We're going to look at 2 versions. One that makes use of inheritance, and the second version is going to be a rewrite that does make use of inheritance. So let's run the thing first. Okay, that's happening fairly quickly, but what that's simulating is that there's a population of rabbits and a population of foxes. And the rabbits are obviously breeding, and the foxes are breeding, but the foxes are also feeding on the rabbits. So if we reset and rerun this, initially the brown ones are the rabbits and they outnumber the foxes. The blue dots are the foxes. And if you, whoa, that was really quick. Okay, the foxes are killing all the rabbits very fast. If you run these, you start to see how the populations start to affect each other. So like I said, the rabbits are breeding, so they should be creating more and more of those, but at the same time, the foxes are eating the rabbits and also breeding. So depending on the balance of the populations and how quickly one species breeds relative to the other one, how fast one eats the other one, you're going to get different patterns emerging in here. So this is this is an example of what's called a cellular automaton. So these are each of the cells is an agent that obeys a certain set of rules, simple rules, like each agent may have a lifetime, and depending on where it is in its life cycle, it might breed or it might start feeding, or then eventually dies off. The foxes will have some rules about if it's adjacent to a rabbit, then it can eat it. Right? So each type of agent is controlled by a fairly simple set of rules. And then you cycle, so in one cycle, you're going to look at every cell in that field, execute the rules that govern each of the agents, and then cycle through again and again and again and again and keep repeating until eventually you either have come up to a fixed generation number, or it might be that you reach a stable state where all the population dies out, or it reaches equilibrium where there's not much change. Okay? So we're going to look at this program and try to understand mostly how the rabbit and fox classes work. There are a couple of classes like simulator view that are to do with the drawing and display. We're not going to look at that yet, but hopefully we'll have enough time left in the semester that we'll look at basic graphical user interface design, so you start to see how that sort of stuff is done. But we won't be doing that this week. In the tutorial, now I think the COMP1400 guys are a little out of sync, but for the tutorial accompanying this one, you're going to look at this code and you're going to try to work out that there's commonality in the code between the rabbit and the fox, and your job in the tutorial is going to be to create a superclass of these guys, which is an animal class that shares the commonalities between these, and keep in the rabbit and fox the rules that are specific to each of those. Okay? So we're first going to have a look in reasonable detail at some of the code for these things without this additional inheritance, and then your job is going to be to try to figure out how to implement the inheritance. Okay, so there's our structure. The main classes, like I said, that we're interested in the lectures is this sort of stuff, and if you're interested in the GUI things, you can have a look at that separately. But fox is going to model the fox, obviously the rabbit models the rabbit. The simulator manages the whole thing. So like I said, the purpose of the simulator is to create a loop where we scan every cell in this field, each cell representing or containing one of the agents, whether it's a fox or a rabbit, execute the rules governing those two things, and then loop over and over and over again to allow the evolution of the whole simulation. So the field is just going to be it's a class that contains a two-dimensional array, which corresponds exactly to what we saw on the screen. The location is another class, which is the XY position in the field. And then these other guys, like I said, are mostly just to maintain the graphical interface. All right, so that's what we saw. All right, let's have a look at the main fields inside the rabbit class. So I only got the main things here. We want to know how old the rabbit is, because that's going to govern breeding, whether it's going to die, when it's going to die. And we obviously have to know whether it's alive or dead. We have to know where it is. So which field it's in, so we have a reference to the field, and also know its position within the field. Right? So we create one class to contain the field, which is the 2D array, and another class to contain the XY position within the field. Inside the rabbit class, we're going to have some methods. The main one being called run. Now, what will happen here is that every time we go through the simulation loop, right, remember we're looping through, and every time we go through the loop, we're scanning the field, every cell in the field, and getting each one of those fields to update if it's occupied by an agent. Run is the method that the simulator will call each time it visits this agent. Okay? So if we've got, say, this guy here, then the simulation loop is going to go through, in one loop, it'll scan through left to right, top to bottom, every cell. And in any occupied cell, we look at what type of thing is in it. And in this case, say it's the rabbit. And we'll call the run method on the rabbit, and that'll execute the rules for that one simulation step for the rabbit. And then it'll repeat the whole thing over and over again. So depending on whether it's occupied by a rabbit or a fox, we'll call different methods to give us different behaviors. One scan of this whole field to do the update is like let's say it's 1 year, one time tick. So for both the rabbit and the fox, every time we do one scan or one sort of big loop through the simulation, we have to increment the age. Right? So it's one of the operations we've got to do. So we increment the age, and that'll tell us whether either the rabbit or the fox are old enough to breed, or if they're old enough to die. And also, when we go through also, where there's a sort of breeding rate, so that we can randomly create new rabbits in there as well. Sorry, yeah, well, based on the number of existing rabbits already. Okay. So some simplifications. We don't try to, so we're just assuming that all of the cells are able to replicate. So we don't try to simulate male and female and sort of get into more complicated reproductive things. We're just assuming that any cell is capable of replication. We're also assuming that they reach a certain age and they just all fall over and die. A fox is similar, has similar fields. It's got an age as well, which ticks up every time we go through the thing. We have to know whether it's alive or dead, location, field. So all of those things above are the same. The only difference is that the fox has to maintain a certain food level. And if it goes below that, it'll die. And to maintain it, it's got to try to find rabbits to eat. Okay? So here, when you were looking at for the tutorial and doing your writing your animal superclass, the obvious thing to look at between this slide and the previous one and this one is what are the shared fields? Right? So if you're trying to separate this out and create a new animal superclass that is a parent of both rabbit and fox, which fields can you take out and put into the superclass? Yep. Yeah, everything down to here is common to both. So when we come to look at creating the superclass, all the first four fields and a lot of the operations on them, so the methods associated with them, a lot of those can be pulled out and stuck into the parent class. And only sort of the more specialist things, the things specific to the fox, need to be kept down with the fox. So whereas the rabbit is always on the run, a fox is always on the hunt. So the hunt method is the thing that the simulator is going to call every time through its main loop. Right? So when it goes through the field and it finds a cell occupied by a fox, it's going to call the hunt method. So that the foxes are similar to the rabbits in the sense that they age and they breed like the rabbits, probably not at the same rate. But they have the additional requirement that they've got to feed and they've got to look for rabbits. So the way that that works is that if there is food in an adjacent location, then it'll eat it. Right? So if there's a rabbit in an adjacent location, then that rabbit will get killed and the food level of the fox goes up. Okay, skip some of this. So that's the sort of rough outline of what we have to put into the fox and the rabbit. The simulator class has got to take care of a bunch of other things, like initially it's got to populate the field with some random collection of rabbits and foxes in random number at random locations. It's got to provide a method called simulate one step. Right? Now remember, one step is a scan through the entire field. Okay? So if we go back to over here, I think I'll quit this and start again. There's our initial thing. Now before, I was calling the method run long simulation, which runs through lots and lots of loops of the whole thing. But if I want to, I can call this one here, which is run to simulate one step. So you have to look fairly carefully at this and see if anything changes in a single step. Right? So there's a few changes in that one. And I can keep doing that to look at what happens step by step. Or if I want to, I can say simulate, say, 10 steps and see what happens there. Okay? So simulate is going to give us oh, sorry, wrong one. So simulate gives us, this is the most important one, gives us the ability to do one scan through the field. And then the other methods will call simulate one step depending on how many steps we want to do. Okay. So now let's have a look again at how we might abstract some common stuff. Here is the, when we want to do an update, we have one loop that says, let's iterate through the list of rabbits. So remember what the iterator is? What does an iterator do for us? Anybody? You have seen things like this before. Kind of. If we have something declared as a list, or like an array list, and you want to step through them sequentially, then if you ask for an iterator, so there, like we've got, it is declared to be an iterator over a list of rabbits. And when we say rabbits.iterator, that's saying, give us a handle to one of these iterator objects. And every time we say, give us, if we say it.next, it's going to keep giving us the next thing in the list. Right? So if it's an array list, and we ask for an iterator over the array list, then every time we do an it.next, it gives us the next one in the list, right? And the other thing that it gives us is at the top there, we can say it.hasNext, meaning have we come to the end of the list? Like, do we have a next element or not? If we have a next element, then the for loop can keep going. All right? So the iterator is a built-in class in Java that gives us a way of stepping one element at a time through a sequence. Have a look carefully at the for loop. Normally the for loop has three components to the top line, right? It has normally the left-hand side, the first element in the for loop is an initializer. So it's initializing the variable that we're looping over. The second element is usually a test, so if it's true, keep going. And the third element is usually the increment. So if you say for I starting at 0, as long as I is less than some limit, I++, right? That's the normal sort of form that you would see of the for loop. Where is the third component of that in this thing? Or does it have one? Right, you see that at the end up there, we've got a semicolon and then no increment part. So the reason is that when we do, at the next line, rabbit is assigned it.next, the next method is automatically incrementing the iterator to point to the next method, if there is one. Okay? So when we say it.next, it's doing two things. It's returning the next element in the list, and it's also advancing the pointer in the list, if you like. Right? So that the next time you call next, it's the one following. Okay? So the reason why we don't need the increment in the third component of the for loop is that the next in the body of the loop already does that increment for us. Okay? All right, so that loop is saying for each of the rabbits in the list of rabbits that we've got, call the run method. What's new rabbits? Probably should have a look at that. Well, let's come back to new rabbits. What's the if statement doing for us there? So if not rabbit is alive, what's that if statement doing for us?
Checking if the rabbit's alive or not.
And?
It isn't, they're going to remove
Right, so suppose that either the rabbit has reached its age limit or it's been eaten. We want that object to be removed from the array that represents the field. And similar for the next one. Now we're iterating over the list of foxes. And the same thing, if at the end of that run the fox is dead, then we should remove it from the field. Okay? Let's just have a look at the code. Okay, so here's the actual code. There's the fields. Here's our run method. I'm trying to track down what the new rabbits thing is. Oh, right, okay. So, tell me what the new rabbits list is about. Well, the comment is telling you, but go through in detail that code and tell me what it's doing there. All right, so in the previous in the slide, so in this slide here, we've got this loop that's going through, and it's calling run every time through on these rabbits, but we've got this new rabbits list, so we're trying to figure out what does that do. So here it is. So tell me how that works. Yep. Speak up. Speak up more. Well, let's take us through step by step through that method, line by line. No, before that, what's the first line? No, there's one line before that even. Now, first thing we do is increment the age, right? So every time we're going through and we're looking at one agent, the first thing we do is incrementing the age. Right. So that's why I say step by step, I really mean every single step. All right, then what? So if it's still alive, what do we do? All right, so if new rabbits is a list of rabbits, then the give birth is going to populate that list with some new rabbits. Then what? So these guys don't stay still. Right, remember that the rabbits are running, the foxes are chasing. So if we say the next line, location, new location, what's that doing for us? Okay, so from the name, you can sort of guess that it's going to look for, so if we have a cell, the rabbit might actually be surrounded. Right, all the cells around it may also be occupied. But if we can find a free adjacent cell, so the rabbit can only move, or all the agents can only move one cell at a time in any one step, right? So if you look for, so this is going to look for, pretty much randomly, look for a free adjacent cell. and if it's not, if it's empty, then it'll try to move to it. Right, so when it's the test set new location, when it looks for a free adjacent cell, if it can find a cell, it'll return a reference to that cell. If it can't find anything, if it can't find a free cell, then that call free adjacent location will return null. Okay? So if the location ends up being null, it means that it couldn't find a free neighbor. So what happens if it can't find a free neighbor? Sorry? Who was saying somebody's? You saying that? Set dead, right. So in other words, if it's completely surrounded, if any of the agents get completely surrounded, then we assume that this is overcrowding and it'll starve. So if it can't move to a new location, it dies. Right? So in other words, all the agents, and this will be true for the foxes as well, they have to be able to keep moving all the time. If they're stuck in one location, they die. Okay, what else do we want to look at here? Okay, notice that in the increment age that we called at the start, all we do is increment the age, but we also do this test that if the age is greater than the maximum age, then we set it dead. Now, and set dead, all that does is toggle the Boolean that says it's the is alive field that is set to false. Okay, so here is the give births method. And I want someone to tell me how this works. Do I have any volunteers, or should I volunteer somebody? How does have a look at that for a second, and then tell me how does this method work. And take it step by step. So what's the first step? You made the mistake of looking at me, so now you get stuck. What's the first step there? This line here, what's it doing? Well, no, more than that. The location, that's the location of the rabbit. What's the first thing? We're finding out there if there are any free cells, right? What next? I should say, breed we'll have a look at in a minute. So we have a breeding rate, but we'll have a slightly randomized. So they're not always going to give birth to the same number of things all the time. So if births is the number of births after we call breed, what happens in that loop? What's the condition first? So we got we'll keep looping as long as B is less than births and free is less than size. So what are those two conditions checking? What's births? Sorry? Okay, so that's the number that we've randomly set to be the upper number of births that we're going to have for this rabbit. What's the free dot size greater than 0 checking. Sorry? Well, a bit more than that.
There are free spaces around the rabbit to give birth.
Okay, so when a rabbit gives birth, it's the adjacent cells that get occupied by the offspring, right? So if we decide there are going to be number of births, we have to also check, are there enough free spaces around the rabbit to occupy the new rabbits? So that loop has an upper limit of either births or up to the number of free adjacent cells, right? And then for each one of those, it will go through and let's see, oh yeah. So it's removing, so from the list of cells, it's removing the first one because we're now going to occupy that one. We're creating the new rabbits and adding them to the new rabbits list. And we're doing that for the number of rabbits that satisfy that condition. Okay? All right, we're out of time. So you're going to be looking at this in the tutorial in more detail and, like I said, look at the inheritance. And we'll come back to it on Thursday to wrap that up.